According to 250.104 an interior metal water piping system shall be bonded to an electrode. The proposal involves bonding the water system to the rebar at two locations: firstly, at the far end of the building, over 300 feet away, and secondly, at the service location. This approach fulfills the code mandate for bonding the water system to an electrode. The code does not dictate a specific distance or routing for the bonding conductor, provided it offers a low impedance path to the electrode. The inspector raises a concern that the extensive rebar, spanning over 300 feet, might not offer a sufficiently low impedance path for fault current. The impedance of a path is influenced by several factors, including its length, cross-sectional area, and resistivity. Rebar generally has a higher resistivity compared to copper conductors, and its impedance escalates with length. However, the code refrains from specifying a precise impedance value for the bonding path, instead mandating that the bonding path provides a low impedance path. In practical scenarios, the impedance of a correctly implemented bonding path to rebar is usually very low, even across considerable distances. This stems from the fact that rebar is encased in concrete, which establishes a well-grounded path to earth. Therefore, the method of bonding the interior metal water piping system to the rebar at 2 points complies with code stipulations. Although the inspector's worry regarding the low impedance path holds merit, the impedance of a correctly installed bonding path to rebar is typically minimal, even over significant distances. In summary, the bonding method is code compliant and also furnishes a lower impedance pathway for fault currents. The concept of impedance in grounding and bonding systems is crucial for electrical safety. Impedance, measured in ohms, is the total opposition a circuit presents to alternating current. It is more than just resistance, as it includes the effects of inductance and capacitance. A low impedance path is essential for quickly clearing ground fault. This means that when a fault occurs, the current can return to the source with minimal opposition, tripping a circuit breaker or blowing a fuse to de-energize the circuit. A high impedance path, on the other hand, will limit the fault current, potentially preventing the overcurrent device from operating and creating a dangerous situation. Several factors influence the impedance of a grounding or bonding path. Firstly, the length of the conductor is a major determinant. Longer conductors have higher impedance due to increased resistance and inductance. Secondly, the cross-sectional area of the conductor plays a role. Larger conductors have lower impedance because they offer less resistance to current flow. Thirdly, the material of the conductor affects impedance. Copper is a better conductor than steel, so a copper conductor will have lower impedance than a steel conductor of the same size and length. The connections in a grounding or bonding system are also critical. Loose or corroded connections can significantly increase impedance, hindering the flow of fault current. Rebar, while often used as a grounding electrode, has a higher resistivity than copper. This means that for the same size and length, rebar will have a higher impedance than a copper conductor. However, when rebar is encased in concrete, the concrete helps to create a low impedance path to earth. The concrete provides a large surface area for contact with the earth, effectively increasing the size of the grounding electrode. To ensure a low impedance path, it is important to use appropriately sized conductors for grounding and bonding. The size of the conductor is determined by the size of the service or feeder conductors, specified in the National Electrical Code, or NEC. Proper installation techniques are also essential. All connections must be tight and free of corrosion. Rebar connections should be made with approved connectors and should be properly encased in concrete. Regular inspection and testing of grounding and bonding systems is also important. This can help to identify potential problems before they become safety hazards. Testing can be done using an impedance meter to measure the impedance of the grounding path. If the impedance is too high, the system should be inspected and repaired. In a given scenario, the electrical inspector is concerned that the 300 plus feet of rebar may not provide a low impedance path for fault currents. While this is a valid concern, it is important to consider the overall impedance of the grounding system. The rebar is connected to the service equipment with a 3/0 copper conductor. This conductor provides a low-impedance path from the service equipment to the rebar. The rebar itself is encased in concrete, which provides a low-impedance path to earth. If the connections are properly made and the conductors are appropriately sized, the overall impedance of the grounding system should be low enough to safely clear ground faults. It is also important to consider the type of overcurrent protection being used. If the service is protected by ground fault circuit interrupter or GFCI, then even a small ground fault current will cause the GFCI to trip, de-energizing the circuit. In this case, the impedance of the grounding path is less critical. However, if the service is protected by a standard circuit breaker or fuse, then a low impedance path is essential to ensure that the overcurrent device will operate quickly enough to prevent a dangerous situation. Ultimately, the decision of whether or not the contractor's grounding method is code compliant and provides a low impedance path is up to the electrical inspector. However, based on the information provided, it appears that the contractor's method meets the code requirements and provides a reasonable level of safety. The specific requirements for grounding and bonding are detailed in Article 250 of the National Electrical Code, or NEC. This article provides comprehensive guidelines for establishing effective ground fault current paths and ensuring electrical safety. Key sections within Article 250 address various aspects of grounding and bonding, including system grounding, equipment grounding, and bonding of metal water piping systems. Section 250.4 outlines the general requirements for grounding and bonding, emphasizing the importance of creating a low impedance path for fault currents. This section highlights the need for electrical systems to be grounded in a manner that limits the voltage to ground and facilitates the operation of overcurrent protective devices. Section 250.24 provides specific requirements for grounding alternating current, or AC systems. It details the methods for connecting the grounding electrode conductor to the system grounded conductor, ensuring a solid connection that can effectively carry fault currents back to the source. Section 250.50 covers the requirements for grounding electrode systems. It specifies the types of electrodes that can be used for grounding, such as metal underground water pipes, concrete encased electrodes, and ground rings. This section also addresses the requirements for bonding these electrodes together to form a comprehensive grounding system. Section 250.104 focuses on the bonding of metal water piping systems. It mandates that interior metal water piping systems be bonded to a grounding electrode to ensure that they are at the same electrical potential as the grounding system. This bonding helps to prevent electrical shocks and provides a path for fault currents to return to the source. The low impedance path is crucial for several reasons. Firstly, it ensures that fault currents can quickly return to the source, tripping the overcurrent protective device and energizing the circuit. This minimizes the duration of the fault and reduces the risk of electrical shock or fire. Secondly, a low impedance path helps to limit the voltage rise on metal parts during a fault. This voltage rise can be dangerous if someone comes into contact with the metal part, as it can result in an electrical shock. Thirdly, a low impedance path improves the performance of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small ground fault currents and trip the circuit, preventing electrical shocks. A low impedance path helps to ensure that the GFCI will operate quickly and reliably. In addition to the NEC requirements, there are also industry standards and best practices that can be followed to ensure effective grounding and bonding. These standards provide guidance on the selection of grounding and bonding materials, installation techniques, and testing procedures. One important consideration is the use of exothermic welding for making grounding and bonding connections. Exothermic welding creates a permanent, low-resistance connection that is highly resistant to corrosion. This type of connection is often used for connecting grounding electrodes and bonding conductors. Another important consideration is the use of corrosion-resistant materials for grounding and bonding. Copper and stainless steel are commonly used for grounding electrodes and bonding conductors because they are resistant to corrosion. This helps to ensure that the grounding and bonding system will remain effective over time. Regular inspection and testing of grounding and bonding systems is also crucial. This can help to identify potential problems before they become safety hazards. Testing should include visual inspections of connections, as well as electrical testing to measure the impedance of the grounding bath. If any problems are found, they should be corrected immediately. In summary, effective grounding and bonding are essential for electrical safety. By following the requirements of the NEC and industry standards, and by using proper installation techniques and materials, it is possible to create a grounding system that provides a low impedance path for fault currents and protects people and property from electrical hazards. The role of the electrical inspector is vital in ensuring that these requirements are met and that electrical systems are installed safely. The inspector's expertise and attention to detail are essential for preventing electrical accidents and ensuring the integrity of the electrical system. Remember that specific local amendments or interpretations of the NEC may exist, and consulting with local authorities having jurisdiction or is always recommended for definitive rulings. The provided details offer a comprehensive overview, but real-world applications may require additional considerations or modifications based on the specific installation and local regulations. It is important to stay updated on the latest code changes and best practices in the electrical industry to ensure safety and compliance. Staying informed helps to apply the knowledge effectively and avoid potential hazards or code violations. Electrical safety is a continuous learning process, and staying up to date with the latest advancements and regulations is crucial for all professionals in the field. Continuous education ensures that electrical work is performed safely and efficiently, minimizing risks and maximizing the longevity of electrical systems.